This presentation will integrate the ideal gas law and stoichiometry, our old friend. We'll start by defining the use of standard ambient temperature and pressure and standard temperature and pressure. We will use the ideal gas law to compute molar mass and gas densities, and then we'll perform stoichiometric calculations involving gaseous substances. Actually, we're going to flip that around a little bit. We're going to do stoichiometric calculations first, and then the molar mass and gas densities. So here we go. When you're doing gas law problems, you're going to come across SATP and STP. SATP stands for Standard Ambient Temperature and Pressure. It is at 1 bar, or 1 atm, and 25 degrees Celsius, so room temp. STP, Standard Temperature and Pressure, stands for 1 bar, or 1 atm, and 0 degrees Celsius. I have a minor anecdote on that one if you would like a little laugh, but moving on, let's use these things. What is the volume of 1 mole of gas at STP and at SATP? Okay, so we're going to use PV equals nRT, our ideal gas equation. We have a temperature of 273 Kelvin for STP and 1 atm. So we're going to also use the R that is 0.0821 liters atmospheres per Kelvin mole because atmospheres will cancel with atmospheres. So plug those numbers in, and when we solve, we get a volume of 22.4 liters of gas. Now, there is some important information about this particular value. This is the molar volume of a gas at STP. It will always be 22.4. 1 mole of any gas at STP will have a molar volume of 22.4 liters. It doesn't matter what the gas is. If it's hydrogen, if it's sulfur dioxide, if it's methane, whatever. If it is behaving ideally, it will have a molar volume of 22.4 liters at STP. All right, so let's try this equation again, but at standard ambient temperature and pressure. So we'll have 1 atmosphere. Again, we'll have 1 mole. The R is the same R, but now we use 295 Kelvin for our temperature. When we solve that equation, we get a volume of 24.2 liters of gas. And technically, this is the molar volume at standard ambient temperature and pressure. So we're going to move on from here, and we're going to try to use the ideal gas equation with some stoichiometry. Propylene, or C3H6, reacts with hydrogen under pressure to give propane, C3H8. So we have a balanced chemical equation here, and then it says a sample of 18 grams of propylene requires how many liters of hydrogen when measured at 740 torr and at 24 degrees Celsius. All right, so when you have a problem with this many variables, it is a good idea to highlight and underline things that are important. I've highlighted the starting information, so the initial conditions of the reaction, and I have underlined what we're looking for. So we want to know how many liters of hydrogen. Using our awesome observational skills, we note that we have pressure in torr, but our ideal gas constant is in atmospheres. We have temperature in Celsius, but we need it in Kelvin for all gas laws. And we have been given a mass of propylene and asked about a volume of hydrogen gas. So we have to do some stoichiometry. I like to start by getting the stoichiometry portion complete. So here we go. We have a mass of propylene. We need to convert that to moles in order to use the mole-to-mole ratio in the chemical equation. So that's what we do. 18 grams of propylene divided by 42.08 grams per mole times the 1/1 ratio gives you 0.428 moles of hydrogen gas that we have evolved in this reaction. But wait, there's more. So we need to do those unit conversions that we already talked about. And in addition to that, we know that we need to solve for volume. So volume is equal to nRT over P. Algebra. All right, so from the previous slide, we have our 0.428 moles of hydrogen, and our volume equals nRT over P. We're going to convert pressure to atmospheres. So we use the conversion factor there in the bottom right-hand corner, and we find that we have 0.974 atmospheres of pressure. We also need to convert Celsius to Kelvin. So 273 plus 24 is 297. All right, at this point, we can plug everything in to our original equation. The V equals nRT over P. And when we do that, we get 10.7 liters of hydrogen gas. So when you're doing these problems, we need to make sure that our units cancel. If this had been torr, it could not cancel with the atmospheres in R. If this had been Celsius, it could not cancel with Kelvin in R. See the pattern? All right, so make sure you're doing those things. Now we're going to expand what we can do with PV equals nRT to include molar mass and density. We can relate the ideal gas law to density and molar mass. By now, we're familiar with the ideal gas law as PIV NERT. We also have encountered density equals mass over volume. Density is an intrinsic property for all materials, including gases. So if you solve PV equals nRT for volume, you can substitute that into the density equation. So we solve for volume, and then we're going to put that nRT over P in for the V in the density equation. And we get density is equal to mass times pressure over moles times ideal gas constant times temperature. Now, mass over moles, grams per mole, should be a familiar thing. That is molar mass. And we are going to give molar mass a script-looking M and do a substitution for that. Okay, so density is equal to the molar mass times pressure over the ideal gas constant R times T in Kelvin, always in Kelvin. Okay, so we have a fancy pants script M for molar mass in this section. We can also do an alternative substitution where we use the relationship between moles mass and molar mass directly into the ideal gas equation. So in this case, we start with that N equals M over M, the scripted M, and we put that in for the N in the PV equals nRT equation. And we get PV is equal to mass over molar mass times ideal gas constant R times T in Kelvin. I'm going to keep saying it, in Kelvin. Now I remember this as PIV MERT. Yes, that is silly, but I've kept it in my head for 30 years, so apparently works for me. Use whatever works for you when you remember this. But when I'm having a moment where I can't remember things, I derive this equation by remembering how to get moles from mass. All right, so let's try a problem with gas laws and molar mass. What is the density of a gas with a molar mass of 28.2 grams per mole at STP? So we remember that standard temperature and pressure is 1 atmosphere, 0 degrees Celsius. We can put that in directly with our R, liters atmosphere per Kelvin mole, so we can just substitute into the density equation. And when we do that, we get grams per liter because everything else cancels out. This is a valid unit for the density of a gas. If we look up 1.26 grams per liter, we'll find that this is nitrogen gas. What is the molar mass of a gas with a density of 3.17 grams per liter at STP? So again, we can plug our values into the modified density equation directly. Okay, so this time we have a density, so we have 3.17 grams per liter on the left, and we're solving for molar mass, that's scripted M, on the right. Again, everything is going to cancel out except for grams per mole. All I've done here is algebra. I plugged in the numbers and I isolated that scripted M, the molar mass. After I plug that into my calculator, I get 71 grams per mole, which is the approximate molar mass of chlorine gas. So let's try something with the other equation that we've derived. Okay, determine the molar mass of 4.0 grams of a gas at STP, which takes up 22.4 liters. So in this case, we have a mass, and we can identify that 22.4 liters at STP is the volume of 1 mole of gas under those conditions. Hopefully we recall that the molar volume of all gases at that temperature is 22.4 liters. Therefore, the mass that we see should be for 1 mole, and the molar mass will be 4 grams per mole. But let's do the math anyway. So we're going to plug in our values into the PV equals mmert equation. We have 1 atmosphere at STP. We have 273 Kelvin. We put in our volume, the mass of stuff we have, and our R. And then we isolate molar mass. And when we solve, we get 4.0 grams per mole. Our observation turned out to be correct. That's always nice. Now there are more complicated versions of this that we'll build up to using in our class problem sets. But this is the basic idea. We plug in variables, we isolate what we need. We make sure that everything balances, or rather cancels out. So, summary. Standard ambient temperature and pressure is 1 bar or 1 atmosphere at 25 degrees Celsius. Standard temperature and pressure is 1 bar or 1 atmosphere at 0 degrees Celsius. The molar volume of a gas, the volume per mole, 1 mole, is 22.4 liters. We can do substitutions using the ideal gas law and get that density is equal to molar mass times pressure over ideal gas constant times temperature in Kelvin. We can also substitute our molar mass in for moles in PV equals nRT to get PV equals mass over molar mass times ideal gas constant times temperature in Kelvin. And we need to make sure that the R is in the same units as our P. So if your units do not match, you need to do a conversion.